So what is that you have to understand is what I was trying to explain you is that in our open loop system study, we primarily so far whatever we have studied can be accounted like steady state motion, wherein we define this understeer coefficient to define vehicle tendency, right? So this understeer coefficient will be looks like in different textbook. You should not worry. And this particular lecture and another lecture I would be referring to Thomas Gillespie by the textbook named Fundamentals of Vehicle Dynamics. So here the steering angle would be given in degrees and then your understeer gradient would be dictated by front tire compliance and the rear tire compliance. And how these tire compliances are defined is that slip angle at an axle per G lateral force imposed at that point of time is what is defining your tire compliance. So the unit of understeer gradient is no more radians. What we have considered in this equation is now is going to change as decrease per G, or you don't have your 57.3 multiplication factor, then it can be radians per G. Also you can say, right? So that's how you would define your steering angle. There is also another term called the steering wheel angle. So what is steering wheel angle is what physically the steering wheel of the steering system where driver holds the driving system and giving the input. So that is what is transferred to steering angle through an appropriate reduction mechanism. So there is something called steering ratio. Steering ratio. So this steering ratio is defined as steering wheel, steering angle by steering wheel angle. Angle by steering wheel angle. Steering wheel angle. So if I have to get my steering angle, I have to multiply steering ratio with the steering wheel angle. That's important. Why this is to be mentioned here? Last class we have looked at importantly the steady state gains. So steady state gains are what is your curvature for the given steering angle, or what is your yaw velocity for the given steering angle, or lateral acceleration for this given steering angle. So since steering angle is there at the down, and to get the steering wheel angle, you have to multiply or you have to divide that equation by the steering ratio if it is given in your numerical problem. Please remember that point also, right? So that is what is this, and this is all something what we have already done. We are just recapitulating to get on with the study of suspension effect on cornering. So before that, let us define some important terms called what is static margin. I'm going to explain what is static margin, and then let us see what is Olley's definition of defining vehicle tendency. Then we will look at what is roll moment distribution. And these three aspects is what I'm going to explain you in the remaining 10 minutes of our lecture. So what is static margin? So the static margin is like an understeer gradient KUS or characteristic speed. So how do you define characteristic speed? It is the root of GL by KUS here defined. So either by KUS or this characteristic speed, how you use them to explain the vehicle tendencies, understeer, oversteer, neutral steer. Similarly, there is another metric called static margin. So the static margin is defined as the ratio of two distances, E by L. So what is E is the distance of neutral steer point from CG location, and what is L is wheelbase. So this is what is static margin. So to understand that, let's look at a vehicle drawn. this is the vehicle. You have your CG location somewhere here. And you have something called a point, a neutral steer point. So this point is what is called neutral steer point. By the way, this point would go in a path. The locus of this point, this would vary, and the locus of that point is say this one, and this is called the neutral steer line. Neutral steer line. So what is this neutral steer point on this locus of neutral steer line at any instant? Is that located at a distance from CG by a distance called the E. Right? So this distance is normalized by wheelbase is what is defining static margin. Right? What is defining static margin? So how do you define this point, neutral steer point, that is determined? Neutral steer point is, this is neutral steer point is determined by the point on the vehicle, where a side force will produce no steady state yaw velocity, where a side force will produce no steady state yaw velocity. Right? So that is how you define. So what do you mean by steady state yaw velocity? Yaw velocity is constant. Right? You had in a steady state motion only one equation, Fi is equal to mru, you have seen, where u is forward speed constant and r is steady state yaw velocity. That is also not going to change. That's constant. So you had a relationship r into r is what is equal to u. So this is all what you have seen in steady state motion. In this this is the point when we have also looked at when vehicle is driven in a straight path, there is a side wind gust and its resultant is acting at a point in the vehicle, happens to be at the point here, and that's called a neutral steer point when there is no steady state yaw velocity. That means the vehicle will continue go in a straight line only. So the resultant of side force of wind gust is acting instead of at CG location and it is just behind here, then you would have the yaw velocity. But if the point of resultant is acting at this point itself, called a neutral steer point, then you will not have this yaw motion. So the vehicle would continue in a straight path. That's what is you should understand from this. What is the definition called? The Olley's definition. Olley's definition. So what does this Olley's definition says is this way. Let me draw the vehicle in the top view and their axles alone. So this is front axle and this is front axle and this is rear axle, and I have here a point disturbance force at CG location. So this is my CG location and I have a disturbance force here at CG location. Force at CG location. From the top view, if I see, this is my forward direction of a vehicle. A neutral steer tendency vehicle would go in a straight line like that. Right? If it is a understeer tendency vehicle, would go in this vehicle tendency. If it is a neutral steer vehicle, if it is a oversteer vehicle, that would go into the curve, and that is what we have learned. and that would be explained through this Olley's definition. So how do you represent this through Olley's definition is you see that the static margin what we had here can be positive, can be negative, or can be zero. So what do you mean by positive, negative, zero? The static margin is positive in this case what I have drawn. So the case what I have drawn is positive static margin. When you have your neutral steer point lies behind the CG location, you would have a positive static margin E by L value, and then the vehicle would behave as an understeered behavior. So your vehicle would go in this path. What do you mean by that? That would cause the tire compliance in the front axle to have more slip angle than that of the rear. So the vehicle front axle will plow out. It is called plow out. So plow out. So that would be your understeer effect. On the other hand, if I have my neutral steer point in front of CG location, then I would call that as negative value. And that time, you see that would be of oversteered vehicle where the rear axle will slip out. So here it is front axle will plow out. Hence it is of oversteer tendency. So this is the disturbance direction. Your slip angle will be more here, and that would make this front axle to plow out. So the tendency of a vehicle would be of understeer tendency. So you are expected to correct your vehicle steering. On the other hand, if your static margin is lying, your neutral steer point is lying in front of CG, then what would happen is the rear axle will slip out, and the lateral acceleration would get added with this, and that would cause your vehicle behavior to change into oversteered behavior. And the vehicle is driven at critical speed, the vehicle would spin about vertical axis. So that would what is been defined by Olley's definition. Then what is zero value of static margin? So zero value of static margin is your CG location itself. This point would be CG location itself. What I mean by that, the side force resultant act at CG, but the vehicle would go as it is without any disturbance. That is what is called a neutral steer tendency. So it will not change the compliances in the front and rear axle, and it would be of the same value, so that your KUS is zero at that condition, and the vehicle would be of neutral steer vehicle. So you can say that static margin zero refer to KUS zero in the other way. So like KUS explicitly that you see in a steady state fundamental equation, static margin is the definition when you have a side force acting on your vehicle, and that will not produce any steady state yaw velocity, and that point is what is called a neutral steer point, and that neutral steer point would be having its instant motion along the locus called neutral steer line. So this can be calculated with our understanding of understeer gradient, what we have already studied. So you know that CG is normally represented from front axle at a distance A, and from the rear axle at a distance B. And you can consider now this point, a neutral steer point, is represented at a distance AN. So subscript N here refer to neutral steer point, and then the remaining distance here. So that's B. Like that, if I consider if this AN is equal to A, what I mean by that, it is neutral steer tendency. If this AN is greater than A, it is understeer vehicle. If this AN is less than A, then it is of oversteer tendency vehicle. Like that you can see. So how do I calculate this AN? Can anyone say how can you calculate this AN? This AN can be calculated with the help of your understeer gradient equating to 0. So you know this KUS is related to K3, right? We have defined what is K3, that is defined as this way, right? K3 equals KUS by GL. You remember. So what is K3 called? Stability factor. We are yet to go and look at the stability of the vehicle. This is called the stability factor. You could see that constant term in your characteristic polynomial was expressed in terms of this K3. And this K3 is what is equal to KUS by GL. And what K3 you have defined as this M into BC alpha R minus AC alpha F by L squared C alpha F into C alpha R. Right? This is what is K3. So if I have to get KUS, multiply this by GL. Right? So if I multiply this by GL, then this is KUS. Right? So what is M into G? That's W. So I would have this W into BC alpha F, alpha R minus AC alpha F by L C alpha F, C alpha R. So you know now what is the WB by L? WB by L. So WB by L is the WF, front axle load, and C alpha R and C alpha R goes. I get this W F by C alpha F minus W R by C alpha R. See, I get back my tire compliance, KUS. So this is how these two K3 stability factor, and this is related that we have already seen. I just have to bring in again here for you to understand. To say that when I have tire compliance in the front is more than that of the tire compliance in the rear, that behaves an understeer tendency of the vehicle. If the WF by C alpha F less than this, that represents the oversteer tendency. When they are equal, KES is 0, that is neutral steer tendency. So that we have understood. So let us take this KUS equating to 0 is what is going to help me to calculate what is AN, the distance of neutral steer point from the front axle. So when I make this is equal to 0, this is equal to 0, what will happen? Essence BC alpha R minus AC alpha F should be equal to 0. I put this B as now L minus AN. C alpha R minus AC alpha F equals 0. So if I just take this terms other side, it is L minus AN by C alpha F as A by C alpha R. And I can rework on this further. L by C alpha F on one side and AN by C alpha F on the other side, I can take it. So L by C alpha F equals A by C alpha R plus AN by C alpha F. So I can take this LCM here. So that's going to be C alpha F, C alpha R. And here it is. See, the moment here there is one correction. So the moment I replace B by L minus AN, this A would become AN. So this is AN. So this is AN. So if I take this AN out, I will have C alpha F plus C alpha R, then bracket. So now I can get what is my AN. So that would be taking this on the other side. So C alpha F goes, so L into C alpha R by C alpha F plus C alpha R. So if I have my tire cornering stiffness and the geometry wheelbase, I can calculate what is this AN. If this AN is equal to A, then it is neutral steer vehicle. So that is how you can find out. So how do you get A? For that, you have to find out what is the CG location of your vehicle. There is a geometrical way of doing it. Keep your vehicle on the ramp, and by trigonometrical relationship, you would be able to get or locate what is the CG height from the ground. And the CG height of a vehicle would say what is A and B, and AN you can find, and then you can comment on looking at this value of AN. If this AN is greater than A, then it is positive static margin, referring to understeer tendency of the vehicle. If AN is less than A, then it is negative static margin, referring to oversteer tendency of the vehicle, like that. So this is something what is called a static margin. So I stop at this point, this lecture. So in essence, today's class, you just have understood a new term called static margin. Exam point of view, it is very important. Please go through. And what is Olley's definition? Again, to say what is understeer, oversteer, neutral steer effect. And we have looked at the beginning, the vehicle can be looked at a control system where it is called a closed loop control system or open loop control system. In closed loop control system, it is essentially vehicle driver combination. So vehicle motion driver would absorb, and the way he wants it, he will always do correct the feedback he gets from the vehicle as well as from the environment. And that's closed loop system. The normal driving condition of the vehicle in lateral dynamics is a closed loop system. Open loop systems are the test required conducted in order to understand the directional behavior of the vehicle, and primarily the steady state motion. What we have looked at, you get an understeer gradient is the metric to define your handling capability. And we have looked at what is the definition of steering ratio, and that is steering angle at the tire wheel interaction divided by steering wheel angle of the wheel with the driver's hand. And you require to divide your steady state gain by the steering ratio if you have to talk on what is the requirement of steering angle at the driver hand, right? So with that point, I stop this particular lecture. And in the next class, we will be looking at the role of suspension in vehicle handling. So the effect of role of your sprung mass relative to unsprung mass would create a moment distribution in the front axle and the rear axle. And that distribution of moment in front and rear axle would change the understeer coefficient. And that's what we are going to learn in the next class on Friday. Right? If you have any doubts, you can ask. Otherwise, I'll end the meeting.